Hello, Anatomy students. Mr. Gripper coming at you here from room 227, West Clermont High School. And today in our lecture material on the cardiovascular system, we're going to talk about the blood and to change things up a little bit and to really get in those likes and subscribers. I'm going to wrap the lecture material to the tune of Flo Rida's Low. No, I'm not. I'm just kidding. I'm not going to do that. I'm just going to talk like normal. So hopefully I had you going there. So let's go ahead and get started. All right, everybody. Welcome to video lesson 3 on the cardiovascular system. Today we're going to talk about the blood. So first, let's discuss the characteristics of blood and their functions. Blood transports oxygen, carbon dioxide, nutrients, heat, waste, and hormones. So everybody always thinks that one of the most important things, and it is important, that blood will carry is oxygen. That is a large part of what it does. But if there's a part of the body that needs something, a hormone or nutrients, or even to be kept warm, the blood is what does it. And we'll talk more about how blood is circulated and how we maintain our temperature and hormone levels and so on and so forth. But it's not just an oxygen carrier. It helps regulate our body's pH, our temperature. It keeps us warm and will keep us cool when we need it, and will maintain the water content of our cells. The physical characteristics of blood. So usually when people hear blood, they just think blood is just the one thing. Blood is a tissue, which means it is made up of different cells. We remember, hopefully, from the tissues unit, it is a type of connective tissue. And that means, by the structural levels of organization, that molecules make cells and cells make up tissues. So there's more to blood than just calling it blood. It has a viscosity greater than water, which means it's thicker than water. So that old adage, that blood is thicker than water, that old adage is true. It maintains a constant temperature. Typically inside our bodies, it's going to hang right around 38 degrees Celsius, which is just a tad higher than our normal body temperature. And here, lately, we've been taking our temperatures quite a bit, looking for COVID symptoms. Everybody says at 98.6, that's an average. That's a normal core body temperature or an average body temperature. Some people may run just a little warmer than that, based on all the temperature readings that I've been doing with our high-tech thermometer at home. I run a little cooler. My temperature almost always comes in at about 97.3, 97.4. So it kind of depends on the individual, but we're usually up there, and that's Fahrenheit, of course. We're usually up there in that high 90s mark. So 37 degrees is 98.6, and that is what is deemed as our normal core body temperature. So your blood, keeping your body warm, is going to obviously have to be warmer than your core body temperature. Blood constitutes about 8% of your body weight. Let's go back and talk about the pH. The pH of your blood is about 7.35 to 7.45 on that pH scale. And of course, I'm sure we all remember that pH goes from 0 to 14, with 7 being neutral. Anything over 7 is slightly basic or alkaline, and anything below 7 is slightly acidic. So our blood is just slightly basic, just a tad over neutral at 7.0. Back to the mass of our bodies and the volume. It's going to be about 8% of our total body weight and have a volume of 4 to 6 liters. So think about if you were to drain an adult, you're going to possibly get about 3 2-liter bottles worth of blood coursing through their veins, which, when you and a mortician or a coroner, when they embalm a body, they will extract all that blood, and that's what they're going to end up with, somewhere between 4 to 6 liters. So give or take, you say about 5 liters of blood, I would say, would be the average. Obviously, a larger person, a taller person, is probably going to have a little bit more blood than, say, someone who's coming in right around that 5 foot 0 inch mark. Blood consists of about 55% plasma, and then 45% is going to be the formed elements. Plasma is the liquid component of blood. It is the stuff that all the formed elements will be dissolved or suspended in. So most of blood is going to be red blood cells and plasma. That's going to make up of about 99.9%, somewhere around there, of your blood is going to be red blood cells, also called erythrocytes, or your plasma, the fluid that is your blood. Everything else is going to make up at less than 1%. That includes platelets and the white blood cells, the part of your immune system. Plasma is about 91.5% water and 8.5% solutes. Hopefully we remember from chemistry class that to make a solution, you have to have a solvent and solutes. Solvent is what the solutes dissolve into. So water is the universal solvent. So plasma is mostly water with a few solutes dissolved into it. Most of what's going to be dissolved into that water will be proteins, some hormones. There will be a small amount of respiratory gases. Electrolytes will be there, and some waste products. The formed elements include the red blood cells or erythrocytes, leukocytes or white blood cells. Of course, they function in immunity, and thrombocytes or platelets. Those are the small, very tiny little objects in the blood that allow our blood to clot. Red blood cells or erythrocytes are biconcave discs without nuclei that contain hemoglobin. Our red blood cells are unnucleated. They have no nucleus, and they are a biconcave disc, which means they are concave on both surfaces. If we look at this picture here, you can see the concave here. It's concave here, and you can see that concave right there. It also will be concave on the other side that we can't see. And that is where the term a biconcave disc comes into play. The reason it is a biconcave disc is because that extra little dip that it takes right here and comes across and comes up there increases the surface area of the red blood cell, and that means it will be able to carry more oxygen. It will be able to hold on that surface of the plasma membrane of the red blood cell. It will hold more hemoglobin, which will then bond more oxygen and make that cell a little more efficient at carrying oxygen. The reason it's unnucleated is to allow it to be very small and thin. That gives it that biconcave. If you put a nucleus in there, it wouldn't be able to have that biconcave shape and would make it less efficient at carrying oxygen. The function of hemoglobin in red blood cells is to transport oxygen and some CO2. We remember from the respiratory system that only about 23% of the carbon dioxide carried in your blood is going to bond to hemoglobin. The rest of it will be carbonic acid in the plasma. Hemoglobin molecules are specialized components of the red blood cell plasma membrane, which combine with oxygen or CO2 in this transport process. And as we talked about in the respiratory system, carbon monoxide will more readily bond to hemoglobin than oxygen will. So in an area with high levels of CO, you could suffocate, even though there's still oxygen in the atmosphere. The carbon monoxide more aggressively bonds to hemoglobin than the oxygen will. It just outcompetes. Hemoglobin would rather grab the carbon monoxide molecules instead of the oxygen. And that's not good for you and the longevity of your life. So if you have natural gas in your house, please, please, please make sure you have a carbon monoxide detector. The red blood cells only live for about 120 days because of the wear and tear on their plasma membranes as they squeeze through blood capillaries. Your capillaries are microscopic. Most of them are only large enough. The inside diameter is only large enough to let one red blood cell through at a time. So they have to line up and make their way through the capillaries. They're very, very thin, and the red blood cells get squeezed through them so that they can dissolve and drop off their oxygen and pick up CO2 and vice versa when in the capillary beds of the lungs. And because of this, they get worn out. The friction of doing that damages the plasma membrane, and they just don't last. And then as they die, they are cleaned up by the liver and a few other places. Some of the white blood cells will engulf them and destroy them, and then that stuff gets filtered out in the liver and a little bit in the spleen, and then they're regrown in, of course, the bone marrow inside your long bones. A healthy male is going to have about 5.4 million red blood cells per cubic millimeter. Think about a cubic millimeter. That is a box, a square, a cube. That is going to be 1 by 1 by 1 millimeter. I mean, that is a tiny, tiny little box. And I mean, that's going to hold what? A drop of blood. And in that drop of blood, an average male is going to have 5.4 million red blood cells. And that gives you an idea of how small they are. And the average female, there's going to be about 4.8 million. Why the difference? I can only venture a guess. I would have to say that since males have a larger muscle mass, maybe they require more oxygen to fuel those muscles and that heavier muscle mass. And that may be why they have more red blood cells per cubic millimeter. But again, I'm no hematologist. I'm just a simple anatomy teacher trying to make his way in the world. The leukocytes, or white blood cells, function in immunity. They are nucleated and do not contain hemoglobin. They are not going to carry oxygen. That is not their job. Their general function is to combat inflammation and infection. White blood cells usually live for only a few hours or a few days. This is a test that they do to find out if you are sick or if you have some type of illness, is they check your white blood. Because when you get sick, your body says, hey, we need more white blood cells. And so your white blood cell count goes up. And it's a test that they can do. If your white blood cell count is up, then they'll know that your body is sending out signals that says there's something wrong inside here and we need white blood cells to fix it. So their lifespan isn't that long. Normal blood is going to contain 5,000 to 10,000 white blood cells per cubic millimeter. So nowhere near the density, nowhere near the number of red blood cells are we going to see white blood cells. I mean, we're looking at roughly 5 million to 5,000. So many, many more times the number of red blood cells than white in the same volume of blood. Granular leukocytes. So we have a few different kinds that are out there. So we'll cover what they do. We have 3 kinds of granular leukocytes. We have neutrophils, are wandering or fixed macrophages, and they engulf foreign invaders and other things that need to be removed from the blood. Hopefully we remember phagocytosis from biology, and that's where the cell engulfs something and destroys it on the inside, kind of like Pac-Man does. Eosinophils combat the effects of histamine, which is what your body releases during an allergic reaction. They phagocytize antigen and antibody complexes. So when a cell is targeted with an antigen, the antibody then will target that cell, and the eosinophils will clean it up, to explain it very simply. And lucky for us, they will combat parasitic worms. So, if you don't want worms living in your body, then hopefully you have a lot of eosinophils. Basophils develop into mast cells that liberate heparin, histamine, and serotonin in allergic reactions that intensify the inflammatory response. So eosinophils combat the effects of histamine. The basophils intensify the effects of histamine. And if you've ever had puffy eyes and a runny nose in the spring due to allergies, you know what histamine does to your body. Agranular leukocytes, we have the B lymphocytes and the T lymphocytes. In response to the presence of foreign substances called antigens, they differentiate into tissue plasma cells that produce antibodies. We're going to talk in the next lesson about blood types and the anti-A and anti-B antigens that will be antibodies that your blood will have depending on your blood type. We'll talk a little bit more about how antibodies and antigens work. So hopefully that will clear that up a little bit. But basically, a cell will have an antigen, and that will call for a antibody that will fight and attack it. And that's where the B lymphocytes come in. The T lymphocytes, also known as killer Ts, they destroy foreign invaders directly. And they also, a lot of times, will do so through phagocytosis. They just simply engulf and put that individual in a vacuole, and then they release the lysosomes on them, carrying the digestive enzymes and then they'll break it up with basically acid on the inside. And that's why they're called killer Ts. And coincidentally, those are the parts of your immune system that the AIDS virus looks for. So AIDS attacks the one part of your blood that can actually help cure you from that virus. Thrombocytes or platelets are the blood clotting agent of the body. They are disc-shaped structures without nuclei. They help repair slightly damaged blood vessels and promote clotting. So when you get a hole in your vascular tissue, the platelets will plug that hole from the inside with a blood clot and will stop you from bleeding. At this point, this is typically in a class where I will ask, does anyone know what the genetic disorder is that prevents a person from having their blood clot? This person that has this disorder, usually males, their blood doesn't clot. And so a simple cut can be life-threatening if they don't receive medical attention. And of course, hopefully, as you're watching this, you're answering to yourself the name of this disorder, and it naturally is hemophilia. Normal blood is going to contain about 250,000 to 400,000 platelets per cubic millimeter, way more than white blood cells, but still a far cry short of the red blood cell numbers. And the platelets are much smaller than the red blood cells. So number one, they're not going to take up why they don't take up as much volume, because they're really, really small. And the other reason is there's nowhere near as many as there are red blood cells. They have a lifespan of only 5 to 9 days, so they're not going to last very long, about a week in your blood, and then they will also be filtered out by the liver and as they begin to die off. And the white blood cells, aged or dead platelets, are removed by macrophages, which we just talked about when we talked about the white blood cells, and they are also cleaned up by the spleen and liver, as I just mentioned. And I think that's going to do it. All right, that's it. Sorry it wasn't very musical. That's all we have for video lesson 3. As always, if you have any questions, shoot me an email. And don't forget, click like and subscribe. Thanks for watching. We'll talk to you later.